Hi. So my name is Levi. I come from LilyPad and Bacalhau, which is an open source distributed computing platform built at Protocol Labs. Bacalhau is basically running any arbitrary Docker or WASM image anywhere from IoT devices all the way up to GPU servers. The point is to bring the compute to the data rather than the data to the compute. Sorry, the compute to the data, rather than the data to the compute. So if you have like a 5 petabyte or terabyte or whatever data set over there, you can send the compute to where it is and have it computed there and then get the result back. And LilyPad is the incentivization layer on top of this. And it's basically a permissionless, trustless, two-sided marketplace for compute. That's the simplest way to put it. So basically, in these environments, because they're trustless and permissionless, you have to have some kind of protocol for verifiable computation. So you basically need to know if I send this task to that node, how do I know that that node is giving me the result back correctly? And so there's a few ways of, verifiable computation is a very large field with a lot of research, associated research. We have, of course, cryptographic protocols like ZK, zero knowledge proofs. We have trusted execution environments and so on. Right now, we're focusing primarily on verification via replication or optimistic verification. So basically, you double check the work however often on some other node and compare the results. And then the question is, there's a lot of kind of game theoretic problems in that. So like, of course, how much collateral do you have to put up? How often do you check? How do you prevent the node that you check with from colluding with the other node? And so there's a kind of a rich problem space there that, impossible to cover in 10 minutes, but it's very, very interesting. And there are other kind of related questions also, like how do you actually price these computations? And then how do you schedule if you have like kind of more complicated tasks than just running one computation against one node and so on. So basically, the overall approach we're taking to this is we're taking some inspiration from the revelation principle, which is a central result in mechanism design. And so I want to be really clear, we're taking inspiration from it. We're not using the revelation principle. We're not dealing with social choice functions or anything like that. But basically, the idea is that we want to design autonomous agents that represent clients and compute nodes in this two-sided marketplace to maximize their utility, right? And so, utility maximization is a common assumption in game theory. We know that, in real life, we have these questions like, does utility even exist? Are we even capable of understanding what our utilities are? If they do exist, can we actually enact them rationally and so on and so forth? But in, two-sided marketplaces where, you have kind of relatively restricted environment, you can actually say, yes, we want to maximize, I want to minimize my cost based on getting this result back from a particular period of time, or I'm a compute node, I want to get the most money I possibly can for computing this task. And so we basically want to design these autonomous agents to, to maximize utility, even if that includes cheating, right? So a compute node can say, I want this node to represent me and bring me in the most amount of revenue possible. And if that if that autonomous agent decides, the best way to pull in the maximum amount of revenue is actually to just give a false result to that node, we want to allow the autonomous agent to do that, basically. And then that's kind of the first kind of axiom of this approach. And the second axiom is, all other components of the game should drive the probability of that cheating happening to zero. So basically that, there's kind of a lot of different ways of going about this. There's like different types of commitment devices, different types of ways of putting up collateral. There's different ways of checking with consortiums rather than just checking against a particular node. There's of course differences between if you're a client and you're sending the same task to a particular node over and over versus if you're just sending it out to the wild to any node that you can find. There's all these kind of different possibilities, and it's kind of this very, very interesting and complex environment. But this is the kind of the essence of it, right? We want to have these autonomous agents that are representing clients and compute nodes, And we basically want to be designing a global game such that the probability of any of dishonesty basically is driven down to zero. And so, anti-cheating mechanisms are also kind of fundamentally related to pricing and collateral as well, because whether or not it's worth it for you to cheat is also dependent on how much collateral you have to lose if you get caught, and how much you're getting paid to do a job. And these are kind of intimately related concepts as well. And naturally, in a two-sided marketplace, things are very, very fluid, and you can have fluctuating prices that are a function of the supply and demand of the compute resources on the network. Depending on the time of day and the geolocation, right? So like computation, you can imagine computation being cheaper at like 4 a.m. In particular, or maybe even every part of the world than it is at 4 p.m. And that's also partly because electricity prices oftentimes are much higher at 4 p.m. Than 4 a.m. Especially in hot areas. So it's you basically want these autonomous agents then to actually be able to negotiate over the price, right? You want them to be able to if you have 100 clients that have 100 tasks each, and then you have 1,000 potential compute nodes, there are many options of how to kind of combine them. This is kind of classic, two-sided marketplace, two-sided matching problem, and so on. And there's like mountains and mountains of research on this. They have to be able to negotiate, over price, bandwidth, latency, the time to accomplish a task. There's like a very wide range of kind of aspects of the computation that these agents are going to want to be able to negotiate over in order to kind of derive the maximum utility for their respective humans, basically. And there's been, going back to especially in the 90s, there was tons and tons and tons of research on distributed AI, especially negotiating overpricing and scheduling. And it's really interesting in that, we had these kind of like multiple AI winters, and, this kind of research, maybe it was kind of used in industry here and there for scheduling in data centers, or for, maybe scheduling in kind of factories and so on and so forth. But it didn't really hit the public conscience in terms of what it could do. We're living in a different world today. With ChatGPT, with Llama being open source, Stable Diffusion, Midjourney, etc. We're living in a fundamentally different world of capabilities and all of the prior research that kind of that was happening before these AI winters in the 80s and 90s and in the noughts. We now see that we've kind of overcome that hump in terms of computational power available to actually kind of enact these ideas in real life. And it seems like that's going to be true for distributed computation as well. Distributed computation, it probably hit the public conscience most prominently with SETI at home in the late 90s and early 2000s, and with BOINC and other kind of folding at home and other distributed computing platforms, but then it kind of fell to the wayside and so on and so forth. And so we're living in a kind of fundamentally different world, and there's massive new opportunities for this. So one last point before I go to questions. So for complex compute tasks, this is kind of, it's just to give you a flavor of how complex this can get, how interesting it can get. A client may need to negotiate with pools and coalitions of nodes, right? And that gets really complicated because setting aside the anti-cheating stuff, when you're negotiating with a bunch of nodes at the same time, do you have one central node that is orchestrating all those other nodes, or you're negotiating with all those other nodes at the same time? How do those other nodes check that within their coalition that the computations are being done correctly? You can, by the way, going back to the anti-cheating mechanisms point for a second, you can have prediction markets for, is this node going, if it gets checked, is it going to be caught cheating and so on. But then again, you have to account for collusion problems and so on and so forth. So that's basically an overview of, where autonomous agents can be used in these environments. And yes, I'm going to go to questions. Sorry. I think the questions, Thomas, did you want to ask the questions?
Sure, yeah. So we have one question so far. This is from Richard, who asks, have you tried to run an autonomous agent on a Bacchiao compute node yet?
No, but you're front running me a bit, because I kind of want to. So basically, I'm considering for my own purposes writing like a research agent. And like there's already like open source versions of this. I would probably just fork it and modify it a bit especially when you're talking about research papers. I mean, especially since we're building on top of IPFS and Filecoin, we have access to like massive amounts of storage, and so we can kind of take in massive data sets of scientific papers and so on and so forth, and run computations over them. So I'm considering personally playing with that, but right now we're mostly focusing on actually building out the two-sided marketplace itself, as well as focusing on other kind of more interesting use cases like LoRa fine-tuning, Filecoin data onboarding. I think we just got STXL running recently as well. So we're kind of focusing on those kinds of use cases and building out the two-sided marketplace. The autonomous agent stuff is the goal is basically we need a robust two-sided marketplace first before it makes sense to really start exploring it, exploring more in research terms, because there's mountains and like literally decades of research on this topic. But without the actual infrastructure to have these negotiations, then it's kind of just it will remain in this kind of research area rather than actually being implemented.
Cool, great answer. I have one that I thought of when you were at the beginning of your talk. You mentioned the idea of like utility. I'm very interested if maybe you could talk about defining and measuring utility, particularly how might you change the measurement of utility over time?
So I mean, in this context, utility would basically be, it depends on the context of what the node wants, because different nodes are going to want different kind of results. So your utility could just be a function of purely of price, minimize the price, but that might mean, for example, that your job gets run at 4 a.m, 3 days from now, and it takes 12 hours because it's running on a Raspberry Pi, and like so you minimize your utility, or rather you maximize your utility by minimizing your cost. But if you start including other aspects of utility, like how quickly do you want the result, how much data is being produced, so like what's the cost of the data transfer going to be, up from coming from the other node, and so on and so forth. I'm interested kind of taking this would be a step beyond what I've just described, but if you could describe what you want in terms of natural language, and then have an LLM translate what you want in terms of natural language into a scheduling algorithm, not even necessarily into an algorithm, but a set of constraints that this autonomous agent runs or tries to achieve in negotiation with all these other clients, that's kind of where I think it will probably end up. But we have to build modularly in order to get to that point.
Awesome. Yeah, can't wait for that. Okay, thank you very much, Levi. I'm going to bring up